Hi everyone. We previously discussed the Riccati differential equation and the various methods by which this equation can be solved. In this video, we're going to explain a very classic result related to the Riccati equation. It is Bernoulli answer to the original Riccati question. As we discussed, the equation known as Riccati differential equation is as follows, but Riccati was actually concerned with a simpler form of this equation, and specifically he wanted to know for what values of n can this equation be solved using algebraic, exponential and logarithms. Bernoulli came up with the answer very quickly, and we are going to explain his thinking. Also note that this same very equation is written in slightly different forms in different articles and books. For example, most commonly in this form. Bernoulli himself dealt with this form. These forms may look different, but they are equivalent. As we know, moving constants here and there changes nothing. Right, so where did Bernoulli start? With 0, of course. If you plug in 0, you see the equation is separable and hence can be solved by separating variables, y on one side and t on the other side. Now we need to find other values of n, so Bernoulli next showed that the Riccati equation can be transformed into another equation of the same form but different n, where this n is related to the previous n as follows. We are going to see the details in a bit, but let's first make sure we understand his plan. Next, he showed that the Riccati equation can also be transformed into another equation of the same form but yet different n, where n is now related to the previous n as follows. Sounds quite trivial, but he has actually demonstrated his result with something as simple as that. So let's see what just happened. We know the Riccati equation can be solved for n equal to 0, as we just discussed. Next, we know that there is a transformation to another n. So if we substitute 0 for n in the second equation, we infer that the equation can be solved for this n, which is n equal to minus 4. Now let's plug this minus 4 in the other transformation, and if we simplify, we see the equation can be solved for n equal to minus 4 divided by 3. Now clean the slates and plug this new n into the second equation, which we can simplify to get minus 8 divided by 3. So the equation can be solved for n equal to minus 8 divided by 3. Now substitute this for n in the first equation. We can simplify the terms in the denominator, and then the 3's cancel, and we get minus 8 divided by 5. If you repeat the process once more, you will get these values. So we get a series of n's. It's easy to see that this series can be represented in symbols as follows, where m is just integer greater than or equal to 0. To verify, if you plug in 0 for m, you get n equal to 0. If you substitute 1 for m, you get this expression with plus minus. And if you evaluate it with minus and then plus, you get this pair, which is what we have at the top right. Next, substitute m equal to 2 and you get this expression, which you can evaluate for minus and plus, and you will get the next two terms. So the symbolic representation is correct. Now this looks like a strange series, but if you plot it, you see it's quite simple. So it is oscillating around minus 2, and it will tend to minus 2 as m becomes large, but it will never quite get there. Easy to see this from the symbolic form, so if you ignore the plus minus 1, then this is just 4m divided by 2m, which is minus 2. So the plus minus 1 is just adding the oscillation. The contribution of this plus minus 1 gets smaller as m increases. So Bernoulli showed that the equation can be solved for all these values of n. So things work, assuming one can demonstrate the two transformations. So that's our next task. The first transformation can be achieved by considering the following set of transformations. Notice the n plus 1 in the denominator is for simplification. Remember, taking derivative will bring n plus 1 down, which will then cancel the denominator. And his derivation, Bernoulli didn't include this n plus 1 because he had plenty of time, but this form simplifies the presentation a bit, so we go with this form. He actually wrote the equation in a slightly different form. We shall see how he might have come up with this transformation in a bit. Now we need derivative of y with respect to t, so let's take its derivative. The derivative of 1 divided by v is minus 1 divided by v squared. dv is good, but dt is not because it represents the old variable, so we need to express this in terms of the new variable. So let's use the chain rule. Now we can substitute for u, and now you can see how handy the n plus 1 in the denominator is, because derivative of t to the power n plus 1 is just n plus 1 times t to the power n, and this n plus 1 disappears even before it touches the ground, so that's handy. And we can substitute this for dv by dt. We need y squared as well, which is easy because y is just minus 1 divided by v. We can now substitute these into the Riccati equation. We left t to the power n as it is for now. We will deal with it and more. Now multiply through by v squared divided by t to the power n. We need t to the power n, so let's rearrange the second equation to get t in terms of u. We need n instead of n plus 1, so we can just raise both sides to the power n divided by n plus 1, and we can see why Bernoulli used a different form of the second transformation equation. We can now substitute for t to the power n. Notice t is downstairs, so this is why the sign changes to minus. And now remember, minus n divided by n plus 1 is what Bernoulli labeled capital N. We can relabel the coefficients as well because they're just constant, so we get the Riccati form, and we have shown the first transformation. So let's move to the second transformation. Now consider the following set of transformations. As before, we need derivative of y, so let's differentiate the first equation with respect to t. B is constant, eta and zeta are variables, so we need to apply the product rule to the last term, and that's why we get 3 terms. Now we have the 3 derivatives with respect to t, but we want everything to be in terms of the new variables, eta and zeta, so the chain rule is our friend here. And we can also use the second equation. First, let's write zeta in terms of t, so we just inverted the relationship. Then take derivative with respect to t. Derivative of 1 divided by t is just minus 1 divided by t squared, and 1 divided by t squared is then just zeta squared, so that's one sorted. Next, use the chain rule to write derivative of eta with respect to t in terms of derivative with respect to zeta, and we just found that the derivative of zeta with respect to t is just minus zeta squared, so we can replace the derivatives with respect to t in our expression. We just replace derivative of zeta with respect to t by minus zeta squared, and the derivative of eta with respect to t by minus zeta squared times derivative of eta with respect to zeta, which came about because of the chain rule we used. We can substitute this for dy by dt, and then we can substitute for t to the power n from the second equation, and we leave y squared as it is for now, but we will deal with it shortly. We need y squared, so we just apply a plus b squared formula and then substitute this for y squared. Next, get rid of the brackets and hope for cancellation of terms. So these two cancel and these terms cancel as well, and the equation simplifies. Now just divide by zeta to 4, and you see we get the Riccati form but with a different index, which is what we wanted. So we have shown the second transformation, and we had to agree with Bernoulli that the equation is solvable for any value, any series. We saw the limiting value of the series of the indices given by Bernoulli is minus 2, but the limiting value can't be reached via its transformation. However, the good news is the equation is solvable for n equal to minus 2, and this result is due to our old friend Euler. To see, consider the following transformation. So we are changing one variable now and t stays. So we know the drill now. Take derivative with respect to t, and we can substitute for dy by dt, and then for y squared on the right hand side. Now multiply through by t squared, and then just rearrange the terms, and we can see the equation is separable. So the equation is solvable for the limiting value as well. So we have the series of n for which the equation can be solved in finite terms, in terms of the algebraic, exponential, and logarithm. But as you would have noticed, this doesn't prove that these are the only values for which the equation is solvable. There might be more values, right? But luckily, the converse is also true, though it would take a century for someone to prove the result, and that guy name is Liouville. But that's a topic for another day. So I hope you enjoyed the video, and I look forward to seeing you in the next.